Welcome to topic 7.4. We're going to continue looking at Lewis structures, and now we are going to study the ones that have exceptions to the rules. So for this particular lesson, just like before, periodic table, polyatomic list, both of those sources will be useful. So everything that we've done up to this point in 7.2 and 7.3, our goal has been to complete not only the octet of the central atom, but of any outlying atoms. And we did that through single, and in some cases, if there were not enough electrons, double and triple bonds. And so there are some exceptions to the rules where the octet is not always followed with having just 8. And so we're going to first look at incomplete octets, meaning elements that are okay with having less than 8 electrons. And those two are beryllium and boron. The reason why these two are happy without a complete octet is going back to electron configurations. So essentially up to atomic number 5, all of those elements are going to go towards the helium configuration, which would be 1s2. So they are content with having, again, an incomplete octet because of what happens with their electron configuration. If you look, beryllium is in family 2. It's an alkaline earth metal, has 2 valence electrons. And boron is a metalloid in family 13. And those are the 2 elements you are going to be on the look for, as those are the 2 that primarily we study that will have that incomplete octet. So our first example is beryllium hydride. Notice that this one does not have prefixes with it, so that means we need charges and we're going to cross. So beryllium, because it's an alkaline earth metal, is Be with a +2. Hydride is hydrogen with a -1. So hydrogen's kind of odd. Hydrogen can do one of 2 things. It could be +1, -1. It's very fluid in terms of what it can do with its 1 valence electron. So we get a formula of BeH2. So the next thing we need to do to make a Lewis structure is we need to know valence electron total. So beryllium, we know, has 1 valence electron, and hydrogen we have 1 beryllium in the formula. I misspoke there. And hydrogen, we have 2 of them. Beryllium has 2 valence electrons. Hydrogen has 1. So our grand total here is 4 total valence electrons. So when it comes to drawing the Lewis structure out, we have to select our central atom. So that's going to be beryllium in this scenario. And we'll attach our 2 hydrogens to that central atom. If you remember, that single bond represents 2 electrons, and hydrogen's good with the duet. So it's an exception with that 2 electrons. And here we have 2 4 electrons. Everything is spent. We can't make double bonds. We can't complete the octet. Everything's done. And so this is what the Lewis structure looks like with this octet being incomplete on the central atom. So another instance is with boron here. Here's an example with boron trifluoride. So we do have prefixes here, so that means our formula is BF3. Now when it comes to coming up with electron numbers, we have 1 boron and we have 3 fluorine. Boron has 3 valence electrons. Fluorine has 7. So we have 21 plus 3, 24 total electrons. So when we go to draw our Lewis structure, our central atom is going to be the odd man in the middle. In this case, it's going to be boron. And we can see that we'll have 3 fluorines. And what I'm going to do is start completing the octets of my outlying elements. And now that I've done that, I can see that I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So all of my electrons are spent. So I've done that. We can see that now everything is content. Boron, again, is not going to form a double bond between that and fluorine. It doesn't have that capability like oxygen and nitrogen. Again, it all goes back to energy levels with the electron configuration. So we're going to just leave boron incomplete, and that is a okay electron, not electron configuration, but Bohr model. So there's other exceptions to those rules. So not only can we have some that are below having a full octet, but things like phosphorus, sulfur, chlorine, arsenic, selenium, bromine, krypton, xenon, those are elements that tend to have an expanded octet. So expanded meaning going past 8 electrons on that central atom. So when we talk about the octet, like in the first section, incomplete, it's all about what's going on with that central atom. So the central atom in these scenarios can go past that 8 valence electrons because of the total number in it. And it goes back to configuration. So in period 3, we are now adding more and more energy levels and places in their configuration. And so there's instances where we can go past that for atoms. So here, the very first one we have is phosphorus pentafluoride. So phosphorus fluoride, we have 5 fluorines with that prefix. So the very first thing that you should see is oftentimes to recognize something that has a expanded octet is that you have more than 4. So basically most of the things we've been working with would have been like PF4, where we have 4 fluorines to attach that central atom. So a way to help recognize that it's an expanded octet is we now have 5 fluorines going with that central atom. So phosphorus, we have 1 of them. Fluorine, we have 5. Phosphorus has 5 valence electrons, and fluorine has 7. So we have 5 times 7 giving us 35, plus another 5, 40 electrons to spend. So when we go to draw the Lewis structure here, phosphorus will be my central atom. I place my surrounding fluorines, and there will be 5 of them then on this example with the expanded octet. So now I've used 5 times 2, so 10 electrons. So now we're at 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. So when we look at our numbers here, we can see that we had 40 electrons to spend, so that's correct. We've used all of our atoms. And so again, what we now have is the central atom has expanded, and it is okay to have 10 electrons around that central atom to be, again, to keep everything from getting used, or making sure all 40 electrons are used. So here, our next example is xenon tetrafluoride. So xenon is an alkaline, or excuse me, not an alkaline earth metal, but a noble gas. And so there are instances where I told you noble gases, they don't react. We can actually make compounds with noble gases, but they don't occur in nature on their own. They have to be done in a lab, typically under high pressure, in order for them to make the compound. And then from there, they're not a stable compound typically, because of the fact that the noble gases tend to be inert. But again, we can make them form compounds. So xenon tetrafluoride is one that we've produced. So xenon, because it's a noble gas, has 8 electrons, and fluorine has 7. So we have 4 times 7 giving us 28, plus another 8, we get 36 electrons to spend in this scenario. So our central atom, odd man in the middle, so xenon is going to be placed in the middle, and we can see that we should have 4 attached fluorines. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so I've only spent 32 electrons. In my problem, I have 36. So we have to use all of them. We can't just leave electrons out of the diagram. So then I know I have 4 more electrons, or 2 more pairs. And so this is where they have to go on that central atom. The extra electrons will always go there. So in the previous example, that extra electron set was actually a bonded fluorine. In this scenario, those 4 remaining electrons are going to be a lone pair on the xenon. So I'm going to place them kind of diagonal here, off kilter with my bond, so I don't lose track of them. So that gave me 4 more electrons to get to that 36. So this part is good. All the fluorines are good with their complete octets, and then xenon, that central atom, will take on that expanded octet. So the last thing that we can see and work with Lewis structures before we build onto it some more is what's called a resonance structure. And so basically a resonance structure is accounting for the fact that when you draw a Lewis structure, there are different ways in which you can show that material and where the electrons are at. So a resonance structure is by moving electrons, not the atoms. So again, that's going to create some differences. and create different properties for that material because there's different ways it can distribute its electrons. So my example for you guys is for this first one is with sulfur dioxide. So sulfur dioxide is going to be SO2. So when I list them out, I have one sulfur and two oxygens. They're each in the same family here, so each of them have 6 valence electrons. So we have 18 total electrons to spend. So when I go to draw my Lewis structure, my central atom is going to be the sulfur. And I have 2 oxygens. So again, the idea here is when you draw a Lewis structure, we're going to start by trying to use up all 18 electrons. So I have 2, 4, 6, 8, 10, 12, 14, 16. So what I can see here is, yes, I can put my last remaining pair here. And when I do that, all 18 electrons are used. However, this oxygen here on the left is complete. The sulfur in the center is complete. This oxygen on the right is not. So this is not a correct structure for sulfur dioxide. So what I'm going to do here is I know that my central atom is complete and this one is not, that it's going to share a pair of electrons. So the correct Lewis structure to start with here is that we have a single bonded oxygen and a double bonded oxygen, which keeps one lone pair on the central atom. So this is, again, not correct. So the idea here is that this is one way to represent sulfur dioxide. So the resonance structures we show with a double-headed arrow. And so the idea is this is not the only way that sulfur dioxide can exist. What we can do is transfer that double bond over to the oxygen on my left-hand side. So the idea with drawing Lewis structures and going into resonance structures is it's showing 2 different forms in which we can shuffle where the electrons are. So like the previous screen showed, we're not moving atoms. What we're doing here is moving where the electrons are. So these are, again, the 2 options for where electrons can be distributed in a sulfur dioxide. So I have one last example then for this sample, and that's nitrate. Nitrate is NO3 with a -1 on our polyatomic list. We have nitrogen and oxygen, 1 nitrogen, 3 oxygens. Nitrogen has 5 valence electrons, oxygen has 6. So we have 3 times 6 giving me, 18, plus another 5, 23. And then don't forget we have this -1. So when we have that 23 electrons, that -1 means to add 1 more. So it's gained an electron. So 24 electrons is my final number of electrons there. So don't forget that negative means a gain. So to do the resonance structure here, we have nitrogen as our central atom, 3 oxygens surrounding, taking care of 6 electrons. So here we have I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So what I can see is I was able to complete the octets on these 2 nitrogens. I was, however, not able to complete the octet on this oxygen here and this nitrogen if I spend that one last pair. So that last pair of electrons is going to become a double bond. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So all 24 electrons are now in my diagram. And the next thing is I'm looking at octets. Oxygen here and oxygen here are both the same and complete. This oxygen on the far right between the double bond and the 2 lone pairs is complete. And then between the 4 bonds around the nitrogen, it's happy. Now, when we do the resonance structures of something that's an ion, what we do is we then draw in a bracket and put that -1 charge on the outside. So what we do then is we draw that double-headed arrow to then indicate that we have a resonance structure. So we draw another bracket with a -1. When we go to draw the Lewis structure here is we are going to change where that double bond is placed. So I'm going to rotate it to the middle bottom one next. So I'm going to have the one on the left as a single bond. The one on the right is now going to have a single bond. And now our bottom oxygen has the double bond. Now in this scenario, we have one last resonance structure. There's one more way to represent this, and we'll see if I can squeeze this one in here on the far right here. And so when we go to draw that last remaining structure, that double bond, I'm going to just continue to move it, is now going to be on the left side. Yeah, it's really squished in there. So in case you can't pick up and decipher what I have here, I have a double bonded oxygen here with 2 lone pairs. That means the bottom and far right oxygen here have a single bond, both of them including 3 lone pairs. So in all instances, they show the 24 electrons. Octets are complete in all 4 scenarios. And what we've done is we are demonstrating that these electrons can move from one scenario to the next, giving us some different properties. And like I said, that's going to lead into some important properties later on within this unit. So at this point, I have taught you everything related to how to draw a Lewis structure. Now the rest of this unit is going to be application on why in the world does a Lewis structure even matter. And so if you're struggling and needing extra help, it's very, very important that you reach out to me. You can always send me a snapshot of a particular problem you want me to check. We can set up a Google Meet. But again, very important that you reach out to me. So again, good luck with the homework and let me know if I can help.